Hello, my students. I'd like to walk us through an example of a solution calorimetry problem. It's actually number 64 in the back of your book in Chapter 6. We're dealing with an acid-base reaction. And just to rewrite this again, the problem reads, calculate the heat when 100 milliliters of 0.5 molar HCl is mixed with 300 milliliters of 0.1 molar barium hydroxide. Now, if we notice, it is an exothermic reaction, but remember, this is per our balanced chemical equation. Assuming that the temperature of both solutions was initially 25 degrees Celsius and that the final mixture has a mass of 400 grams and the specific heat capacity of my mixture, 4.18 joule per gram degree Celsius, calculate the final temperature of the mixture. I can see I'm given amounts of two reactants, so that immediately should clue us in that this is a limiting reactant problem. Because we're given specific heat and temperature and mass values, that should also clue us in that at some point we're going to be solving and applying this equation. The first thing I'd like to do is determine what my limiting reactant is. So I have 100 milliliters of my hydrochloric acid, converting to liters, and every 1 liter of my solution gives me 0.5 moles. Then I'm going to go ahead and go to this as my product, just because the mole ratio is simply 1. For every 2 moles of HCl, I get 1 mole of my barium chloride. And then doing the same for the other reactant, using the molarity, and then my mole ratio, okay, and then getting my answers. So I get 0.0250 moles of barium chloride from that amount of my hydrochloric acid solution, and I get 0.0300 moles of barium chloride from the barium hydroxide. This is my smaller yield, this is my limiting reactant, so this is what will be actualized. All right, back up here. Now, what I'm told is the mass of my solution, the specific heat. I know my initial temperature. I'm trying to find the final temperature once this reaction happens. So to be able to just have one unknown, I need to know my Q. Well, this is the amount of heat that's released for 2 moles of HCl, 1 mole of barium hydroxide, 1 mole of barium chloride, but I'm only getting this amount of barium chloride out. So if my reaction gives me 118 kilojoules for every 1 mole of barium chloride, but I am only producing 0.0250 moles of barium chloride, then this will give me negative 2.95 kilojoules, which I need it to be in joules for the specific heat, so 2950 joules. Okay, so if I take Q divided by MC, then that will give me my delta T, which is T2 minus T1. So Q divided by MC plus T1 will give me my second temperature. Okay, so plugging in my heat. I'm going to go ahead and do it down here. Sorry that I'm moving things around on us. So, here, negative 2950 joules divided by the mass of the system, 400 grams, times the specific heat, 4.18 joule gram degrees Celsius, plus my initial temp of 25 degrees Celsius will be my second temperature. We need to pause for a moment. Please remember that everything in this chapter is all about the quantity, but the sign. All right. This reaction is exothermic. But what is this heat given to? Sure, I'm producing these products, etc. But what are we actually measuring the temperature of? The water. So, because it's exothermic, I'm going to end up at a higher temperature because the heat is being given from the reaction to the water. And if I keep this negative here, it's going to be lower. So I myself need to go in and make that a positive value. So my 2950 divided by 400 and the specific heat plus my 25 with sig figs, I get 26.8 degrees Celsius as my final temperature. Now, keeping in mind the fractional part of barium chloride that we're producing, keeping in mind the specific heat of water, which is the specific heat of the solution, that small temperature change is definitely reasonable. So yes, we have to know that we are given permission to change signs, and we really have to be aware of what is going on within our solution.